Welcome to the Crazy Hat Chemist. So another video here on solubility. Bam! So we're doing solubility example number 9. It says the common ion effect and solubility. So calculate the solubility of iron 2 hydroxide, which is ferrous hydroxide, in grams per liter in a 2.3 times 10 to the negative 3 molar iron 2 nitrate solution, which is a ferrous nitrate solution. The solubility product constant for iron 2 hydroxide, that is ferrous hydroxide, is 1.6 times 10 to the negative 14. All right, so we do know that iron 2 nitrate, or ferrous nitrate, is a salt, and therefore it dissociates 100% to give you an iron 2 plus ion and 2 nitrate ions, consequently. Okay, the concentration of the iron nitrate is 2.3 times 10 to the negative 3 molar. Therefore, the 1-to-1 mole ratio between the iron nitrate and the iron ion is 1-to-1. Therefore, the concentration of the iron is 2.3 times 10 to the negative 3 molar as well. The concentration of the nitrate, not that we need it for this particular problem, but it is 2 times that value at 4.6 times 10 to the negative 3 molar. All right, so now we know that our salt dissociates 100%, and the common ion here, what we need to do is write the solubility product equation for the iron 2 hydroxide. And that is this right here. And you should see that there's actually a common ion. That common ion is the ferrous ion, which is the iron 2 plus ion. So I've got ferrous hydroxide. It is an insoluble precipitate. That's what's on the left-hand side. On the right-hand side, I got an iron 2 plus ion and 2 hydroxide ions. You should see that those equilibrium arrows lie far to the left-hand side, as indicated by the KSP value of 1.6 times 10 to the negative 14. That is reactant favored. We're going to do an ice table here. That is initial, change, and equilibrium. Now, again, with every single solid, we don't need to include the solid, so we're going to get rid of that. Now, what is the iron ion concentration? Well, it is 2 things combined together. That is the ferrous nitrate and the ferrous hydroxide together. So the common ion is coming from the salt, which dissociates 100%. So that way, I know the iron ion concentration at 2.3 times 10 to the negative 3 molar. What is the concentration of the hydroxide ion concentration initially? Well, it's 0, just like what you would expect it to be for any equilibrium problem. And again, the reason it's not 0 for the iron ion concentration is because you have a salt that is dissociated 100%, and therefore you get the iron ion concentration. Now we need to look at the change. The change is going to be very similar to what we've done before. That is, the solid, don't have to worry about it. If it's on the product side, then I'm going to have a plus sign. And I'm going to be using the stoichiometric coefficients to come up with the values in front of the x. So this is going to be a plus 1x, and this is going to be a plus 2x. We're going to draw a line in the sand and add up the initial and the change columns to get the equilibrium column here. And that is the 2.3 times 10 negative 3 plus x. Okay, that's why I get this for the equilibrium. And then 0 plus the 2x, and I get this 2x here for the equilibrium for the ferrous hydroxide. All right, so we're almost there. We're getting very, very close. Now what we're going to do is we're going to write the solubility product constant expression, and that is the KSP is equal to ferrous ion in brackets, hydroxide ion in brackets, with an exponent of 2 on the hydroxide ion. Hopefully you remember where all those values are coming from. Now what we're going to do is we're going to plug in our equilibrium concentrations into this. That is the iron ion concentration and the hydroxide ion concentration, as well as the KSP value, which was given in the problem right there. The KSP value was given in the problem. The iron ion concentration was given right here, and the hydroxide ion concentration is given right here, all at equilibrium concentrations. So now what we're going to do is we're going to plug this right into here, all those values. On the left-hand side, I have the KSP at 1.6 times 10 to the negative 14. The iron ion concentration is 2.3 times 10 to the negative 3 plus x. And the hydroxide is 2x quantity squared. Now, I don't know if you remember this, but way back from the equilibrium unit, 100 times the K, is that less than the initial concentration? If that is the case, then we get rid of the plus or the minus X. So we're going to apply that rule right here. 100 times 1.6 times 10 to the negative 14, that would be 1.6 times 10 to the negative 12. Is that less than 2.3 times 10 to the negative 3? That is true. So being that that statement is true, we're going to get rid of this plus X here. Now we have a much easier equation to solve, and we do not have a quadratic to solve here. So on the left-hand side, we just have the KSP value. On the right-hand side, we have the 2x quantity squared. We're going to have to deal with that and deal with that squared term. So we have on the left-hand side 1.6 times 10 to the negative 14, and then we have the iron ion concentration at 2.3 times 10 to the negative 3, 4x squared, excuse me. We're going to divide both sides by the 2.3 and the 4, and then take the square root. Okay? So I've divided both sides by the 2.3 times 10 to the negative 3. Now what we're going to do is divide both sides by the 4, and then take the square root. And that's what I'm doing right here. That is the 7.0 times 10 to the negative 14 divided by 4. Take the square root of that. That will give me x. Here is the value for x. X is 1.3 times 10 to the negative 6. So x is equal to the solubility. So this is the solubility, and this is molarity. So that's 1.3 times 10 to the negative 6 molar for the solubility in this problem. Okay, now we need to calculate the solubility in grams per liter. So that's our next step, and we've done this before on previous problems here. So what we're going to do is we're going to take this value for the iron hydroxide, we're going to get the molar mass for iron hydroxide, and we're going to multiply the solubility in moles per liter times the grams per mole, and the moles are going to cancel out. We'll have grams per liter. So we're going to convert this into units of grams per liter. So here we go. We got the molarity and the solubility at 1.3 times 10 to the negative 6 moles per liter. We're multiplying by the molar mass of ferrous hydroxide, which is 89.87 grams per mole. We're going to cancel out our units of moles, and we're going to end up with grams per liter. That value here is 1.2 times 10 to the negative 4 grams of ferrous hydroxide per liter of solution. That is the solubility in grams per liter. Fantastic. Super sad. Okay, if you like that video, give me a thumbs up. Subscribe to my YouTube channel, and I got a great hat here for you. Check it out. Is it an alligator? Is it a crocodile? What is it? I don't know. But I'm going to see you next time for another video. Bye now.